Okay, so let's get started. Hello, everyone. Today we have the pleasure to welcome Perrine Miriot, who's a third-year PhD student at CEA Saclay, and she's gonna present today the first study of the pygmy dipole resonance via neutron inelastic scattering at Ganil spiral 2 NFS. So, Perrine, thank you so much for presenting today, and whenever you're ready.
Okay, thank you, Tanya, and good afternoon, everyone. So indeed, today I will present my PhD work to you, and I will first start with some context and the motivation for this study of the pygmy dipole resonance via neutron inelastic scattering. And first, I will start with a brief reminder of the giant resonances, which are collective vibration modes of nuclei that involve the majority of the nucleons and which have this large cross-section and are present in all nuclei. And the giant resonances transition can be fully characterized by three different quantum numbers: the isospin, the spin, and the multipolarity. And since the majority of the nucleons are involved, the giant resonances have a macroscopic interpretation. And for each set of quantum number at play, we have a given macroscopic interpretation of the giant resonance. Regarding the isospin first, so it is a quantum number that describes the relative motion of protons and of neutrons. So for resonances with an isospin equal to 0, they are called isoscalar, and the protons and neutrons move in phase. Whereas for isovector resonances, the protons and the neutrons move in phase opposition. The same holds for the spin quantum numbers, but this time that describe the relative motion of spins up and down. So electric resonances have spin up and down moving in phase, and magnetic resonances spin up and down moving in phase opposition. The last quantum number is the multipolarity, and in particular the dipole multipolarity, so with L quantum number equal to 1, corresponds to the oscillation of two fluids against each other. If we now focus more particularly on the electric dipole response of nuclei, you have here the typical electric dipole strength as a function of the excitation energy. And in this electric dipole strength, we have the isovector giant dipole resonance that exhausts a large amount of this electric dipole strength due to its large cross-section. And the macroscopic interpretation of this isovector giant dipole resonance is described as the oscillation of the neutron fluid against the proton fluid. It has been observed, however, in this electric dipole response that as we study more and more neutron-rich nuclei, there is the emergence of a low-lying electric dipole strength, and those states have been called the pygmy dipole resonance. So it corresponds to an exotic excitation mode, which is characteristic of neutron-rich nuclei and of electric dipole nature, and which is located at energies below the isovector giant dipole resonance and around the neutron separation energy threshold. And one possible macroscopic interpretation of this PDR is that it may correspond to the oscillation of a neutron skin made of the neutrons in excess against an isospin symmetric core. So there have been many experimental studies and theoretical as well studies of this PDR excitation mode, but as of today, there are still some open questions on its nature. So the first one is concern the collectivity of the pygmy state, that is to say the number of nucleons that are involved in the excitation. Another open question on its nature concerns the isospin nature of the state. So if you recall, the isospin quantum number describes the relative motion of protons and neutrons with isoscalar and isovector excitations. And there are questions regarding this isospin nature of the states and whether or not there is an isospin splitting in the PDR energy region. And one last open question concerns the neutron skin interpretation of the state that I just mentioned. And in my PhD work and in this presentation, I will focus on those two open questions and one experimental approach to try to have more information on these two questions is to use new experimental approaches to pin down the fine structure of the PDR. And one approach is the so-called multi-messenger investigation. So in the multi-messenger investigation, we use scattering experiments, and we rely on the fact that the probe X, which is used, has a certain sensitivity to the excitation. And so if we use complementary probe, we can get complementary information on the nature of the excited state. I will illustrate here the sensitivity of the probes in two ways. So the first one concerns the isospin selectivity of the probes. So for instance, if we consider the gamma prime scattering reaction, it is a probe which is sensitive to both isoscalar and isovector excitation, and which is moreover sensitive to the whole volume of the nucleus in the excitation. On the other hand, hadronic inelastic scattering are probes which are sensitive more to the surface of the nucleus, and which have a selectivity rule regarding the isospin of the resonances that can be populated. And the selectivity rule is written here. So you see with this rule that if we use probes with an isospin equal to 0, like the alpha particle, we can only be sensitive to isoscalar modes. And for instance, protons and neutrons with a spin 1/2 are sensitive to both isoscalar and isovector states. So with this first difference in the sensitivity of the probe, we can extract complementary information of the isospin structure of the pygmy region. Another way in which different probes have different sensitivity concerns the sensitivity to the proton and the neutron contributions to the excitation. So if we just look at our nucleus, there is a relative contribution of the protons and the neutrons to the excitation. So this is encoding in the transition densities that give the transition density of the protons and the neutron with respect to the ground state density, and which are related to the transition matrix elements MP and Mn for respectively the proton and the neutron contribution. Now, when we perform a scattering experiment, the probe that we use has a certain sensitivity to those two contributions that depends on the interaction strength between our probe and the contribution of proton and neutron. And this probe sensitivity is encoded in the BP and Bn coefficients that are written here. So if we now go back to the different scattering reaction that I mentioned previously, for instance, the gamma prime reaction. So it is a probe which is only sensitive to the protons. So it has a ratio Bn over Bp equal to 0. The hadronic inelastic scattering are both sensitive to Mn and MP, but in different relative contributions. So for instance, the alpha particle or the oxygen-17, which are isoscalar probes, are as sensitive as the neutron to the proton. So they have a ratio Bn over Bp equal to 1. And the proton and the neutron probes are complementary probes, since the proton is 3 times more sensitive to the role played by the neutron, whereas the neutron is 3 times more sensitive to the role played by the proton. So you can see with all those different sensitivities of the probe, we can extract complementary information on the nature of the resonance, of the pygmy dipole resonance. And I show here the results of a multi-messenger investigation of the PDR, which was performed in the 140 cerium nucleus. So you have, for various scattering reaction, the observed differential cross-section as a function of the excitation energy. And for this nucleus, the PDR energy region lies between around 3 and 9 MeV. Here it's between 3.5 and 8 MeV. So you have here the isoscalar probes, oxygen-17 and alpha particles, and you have here the gamma prime and the proton inelastic scattering probes. And what you can see directly from those results is that the different probes do not populate the same states in the pygmy region. If we look more closely at the isoscalar probes, you see that there is kind of a threshold above which there are no more states populated, which is here located at around 6.2 MeV. Whereas the gamma and the proton probe, which are sensitive to both isoscalar and isovector excitation, can populate state up to 8 MeV. So this is an indication that, for instance, the high energy states in the pygmy region are more of an isovector, isospin nature. And the goal of my PhD lies in this framework and is to study for the first time the pygmy dipole resonance using the neutron probe, so via neutron inelastic scattering. And as I mentioned before, it is a probe which is really complementary to the proton probe, for which we already have experimental data. So this is the first time that it is done, and it was made possible thanks to the Neutron for Science facility at Ganil Spiral 2. So you have here a schematic representation of Ganil and Spiral 2, with the spiral 2 LINAC here, which can deliver, among others, a proton beam of 33 MeV, which can then be sent into different facilities. And for this experiment, it was sent in the Neutrons for Science facility, of which you have also a schematic view here. And this facility can deliver neutron beams which are unique in terms of intensities. And so that enabled this first study of the PGR. So this facility is separated into two rooms. The first one is the converter room, in which the spiral 2 LINAC proton beam is sent. And you have here a picture of the converter room. And so in my case, we wanted to have a neutron beam spectrum. So the proton beam was sent onto a converter. So at NFS, there are two types of converter, which can deliver continuous neutron spectra or quasi-monoenergetic neutron spectra. So this is the one that we used, and we use for that a thin lithium converter. And the neutron beam is generated via the charge exchange reaction, which is written here. And you have here the neutron beam spectrum that we measured at the beginning of the experiment, and we had a peak at 30.8 MeV. And the intensity on our target was 10 to the 6 neutrons per second. So once the neutron beam is generated, it is then sent into the time of flight room, in which we placed our targets and the detectors. So you have here a picture of the detection of the experimental setup that we placed at the entrance of the time of flight room of NFS. And for this study, it was chosen to use a natural cerium target to study the pygmy dipole resonance in 140 cerium nucleus. So the reaction of interest is the inelastic scattering written here. And we want to detect in time coincidence the scattered neutron with the gamma rays coming from the de-excitation of the cerium nuclei. So we use for this experiment the faster acquisition system. And regarding the detection setup, we used the monster modules, which are liquid scintillators for the detection of the scattered neutron. And we used the Paris array, which are made of scintillation crystals for the detection of the gamma rays. So we also placed here, you can see just below the Paris array, one exogram clover for its complementarity with the Paris array regarding the energy resolutions to help to identify the different reactions that were populated during this experiment. So let us now move to the analysis method. And in order to explain to you the analysis method, I will first show you the result of the benchmarking of the analysis that I did with a carbon target. So we used at the beginning of the experiment a carbon target of the same dimension as the cerium one. And the first benchmarking of the analysis was made with the study of the elastic scattering channel on carbon-12, so which is written here. And the goal here was to extract the differential cross-section for this reaction and to, in this way, validate the analysis procedure for the scattered neutron detection. Because in this reaction, we only look at the detection of the scattered neutron, so only at the monster setup, which is shown here. So for this study, in order to extract the differential cross-section, we want to measure the energy of the scattered neutron to select the scattered neutron that did an elastic scattering reaction. But in the monster module, we cannot directly measure the energy of the neutrons because they only deposit a fraction of their energy. So instead, their energy is calculated from their time of flight on a known travel distance, which is written here, L, via the formula, which is written here. So you have here the time of flight spectrum that I measured in the monster array. So in red, I show all the events that were detected in the monster modules because they detect neutrons, but as well gamma rays. And in blue, you have the events of only coming from the interaction of neutrons and after the background subtraction. And from this time of flight spectrum, applying this formula, I was able to extract for each monster module the energy spectrum. I show here the energy spectrum map, which corresponds here to the monster setup. And here, simply by counting the number of scattered neutrons measured between 26 and 35 MeV, so the region is shown here with the vertical bars, and knowing the incident free neutron flux on target that we measured at the beginning and the target properties, I was able to extract the differential cross-section. So I show here the result, the differential cross-section, as the function of the scattered neutron angle. So the experimental points are the red squares. So each value corresponds to one monster module placed at a given angle. And the experimental points are compared with the curve from the Tyndall evaluated library. So just a small comment on this analysis. So before having those results, there were some additional corrections that needed to be accounted for that I will just flash here. So first, regarding the attenuation of the incident flux on the target, because we used for this experiment a thick target of 3 centimeter thickness. And so this had to be corrected, as well as multiple scattering in the target. And there were also a special treatment for the 2 monster modules here located at 3 degrees, so which are located here, so very close to the neutron beam axis, and that detected direct neutron beam. So they needed a special treatment. But you can see here that finally the result show a very good agreement with the Tyndall prediction, which validated the analysis procedure for the scattered neutron. So let us now move to the inelastic scattering channel, which would be the channel of interest for the study of the PDR. And here the goal of this benchmarking of the analysis was to validate the detection of the scattered neutron in coincidence with the gamma ray via the study of the first 2+ excited state of carbon-12, which is located at 4.4 MeV. And this analysis also had another interest, because from this analysis, I was able to extract an efficiency point for the Paris setup at 4.4 MeV, which was very important because we measured the efficiency of the Paris setup up to 2 MeV thanks to calibration sources, but we did not have points above 2 MeV, and the PDR energy region, as I mentioned previously, is located between around 3 and 9 MeV for the 140 serum. So this point allowed to have a constraint in the pygmy region, and so to be able to extrapolate the efficiency curve. So here, the analysis method for the study of the inelastic scattering channel is to measure in coincidence in time the scattered neutron and the gamma ray. So from this measurement, we have directly the energy of the gamma ray measured in the Paris array. And we can compute from the scattered neutron energy measured in the monster module, the excitation energy via this formula. So simply, it is the incident neutron energy, which is known, 30.8 MeV, minus the scattered neutron energy and a correction for the recoil of the nucleus. But if you recall what I showed at the beginning, our neutron beam spectrum that we had during the experiment has indeed a quasi-monoenergetic peak at 30.8 MeV, but there are also contributions from low-energy neutrons. And so in order to be able here to compute the excitation energy, we need to only tag on reaction that come from the reaction of an incident neutron of 30.8 MeV. And this selection is made thanks to the time of flight of the gamma ray in Paris. So to illustrate this, here I show a schematic representation of the experimental setup. So with here the generation of the neutron beam in the converter, which is sent on the target, and the detection of the scattered neutron in the monster array, and the detection of the gamma ray in the Paris array. And now, if we have neutrons of 30.8 MeV, we know their time of flight to reach the target, and then the gamma ray take also a certain time to reach the Paris array. And so if we plot the time of flight of the events measured in the Paris array, which is shown here, we can select the contribution of the gamma rays coming from the interaction of 30.8 MeV neutron, and that way tag on the incident neutron energy. And those gamma rays here are called the gamma prompt. So once we have the selection, we can plot what is called the coincidence matrix, which gives the gamma prompt energy as a function of the excitation energy. And if we zoom in the 4.4 MeV energy region, we can select the events of interest via plus or minus 3 sigma selection on both energy axes. Now for all the events here selected with this area, I plotted the gamma ray angular distribution, which I show here, which exhibit as expected a quadruple shape with a minimum at 90 degrees and 2 maxima located at plus and minus 33 degrees. So here this angular distribution is fitted with Legendre polynomial. And the last step to extract the efficiency point for the Paris array was to take the integral of this curve and the integral of this curve gave me the total cross-section for the population of the 4.4 MeV excited state with neutrons of 30.8 MeV. And comparing this value with prediction, I was able to extract an efficiency point at 4.4 MeV, which is given here. So here you have the efficiency as a function of the energy. The other points here below 2 MeV corresponds to the points extracted from the measurement with sources. And this curve is fitted with the radar function and is represented with the solid line. And it is compared with the simulated efficiency represented with the dashed line. You can see that there is a quite good agreement with the simulated curve that validated first this analysis procedure and the coincidence between the scattered neutron and the gamma ray, and also the efficiency curve of the Paris array up to the pygmy region. So now that I explained the general analysis procedure for this experiment, we can move to the study of interest on the cerium target. So as for carbon, I first started with the study of the elastic scattering channel, of which I show the results here. So again, the red squares are my experimental points. They are compared with values from the Tyndall library represented as the black solid line, and with values from DWBA microscopic prediction represented with the blue dashed line. And again, there is a quite good agreement between the experimental points and the prediction. And this result is also a result by itself because to our knowledge, it is the first experimental results for the study of this elastic scattering channel on 140 cerium with neutrons with an incident energy above 15 MeV. So this was the first result. Now we can finally move to the study of the inelastic scattering channel and the study of the PDR with the neutron inelastic scattering. So as for carbon, first the coincidence matrix is plotted. It gives the gamma prompt energy as a function of the excitation energy. And in this study, we want to study the PDR state to only select direct decays to the ground state. And so for this selection, we have to take only events for which the excitation energy is equal to the gamma ray energy from the de-excitation of the state. And so this selection is made via a diagonal selection on this coincidence matrix, which is shown here. And the resolution of this diagonal is dominated by the resolution on the energy of the scattered neutron. And you can see that it changes with the excitation energy. And now for all those events, we want to extract the dipole contribution. So first, we can have a look at the energy spectra, both for the excitation energy and for the gamma prompt energy. So if we project here the diagonal of this matrix on the excitation energy axis, we obtain this energy spectrum. So I show here just for the comparison, the projection of all the events in this matrix represented in black, and only the projection of the diagonal of the matrix represented in blue. So you can see that clearly the selection on the diagonal cleans this excitation energy spectrum. So we have in this spectrum several contributions. We see here around 0 MeV contribution from neutrons that did an elastic scattering reaction. So those events clearly correspond to random coincidences because here we gate also on the gamma ray, so it is random coincidences. We see in the PDR energy region an excess of events, which is good, and we see at higher energies contribution from the giant resonances. So we can do the same for this time the projection on the gamma prompt energy axis. So you have here again projection for all the events of the matrix in black and for only the diagonal in green. Here at low energy, we see several contributions that were all identified, also thanks to the exogam clover that we placed, which had a very good energy resolution to tag all these transitions. Again, in the PDR energy region, we see an excess of events, and at higher energies, the giant resonances. So if we look now at the statistics in the PDR energy region, so removing here the linear background, I obtain a total of around 146,000 coincidences in this energy region. And I compared it with the expected number of coincidences. So for that, I used the prediction for the cross-section of the population of one minor state, and I applied to that the characteristic of the setup, the efficiencies, etc. And I obtained from the prediction a total of 60,000 coincidences expected for one minor state. So we see that it's the same order of magnitude, and the experimental value is higher because experimentally we have not only dipole contribution, but also other multipolarities. So now we want in the PDR energy region to select and extract the dipole contribution. But as you can see on those two spectra, we do not have the resolution to see single states. So instead, the analysis was performed for different slices in energy, and I use 200 keV slices in energy for the analysis. And the way to extract the dipole contribution and in general to take the multipolarity of the different excited states is to use angular distribution, which are our experimental observable together with, of course, the excitation energy. So first, I tried to perform the analysis with the gamma rays angular distribution measured in Paris, but unfortunately, there were clearly a lack of statistics, and I was not able to extract information from the gamma ray analysis. However, with the scattered neutron angular distribution, I was able to perform the analysis. And so the analysis was first to plot the scattered neutron angular distribution. So I show here the angular distribution for two slices in energy at 1.6 MeV and here at 5.6 MeV. And we know in this total angular distribution that we have contribution from several multipolarities and also contamination from elastic scattering events from random coincidences. And so this experimental angular distribution has to be fitted with elastic scattering contribution and contribution from the different multipolarities. And to do so, we rely on theoretical prediction that can provide us with the expected angular distribution for the multipolarities. So in this work, the theoretical prediction were first microscopic prediction of the excited state, which were made within the QRPA framework. And so those microscopic prediction gave us the energy, the multipolarity, and the spin of the excited state together with their transition density. So I mentioned it very quickly before. The transition density, they characterize the excitation, and they correspond to the proton and neutron transition density with respect to the ground state densities. And those microscopic predictions were used as an input for the direct reaction model, which was DWBA. And this direct reaction model provided us with the predicted angular distribution that I show here for the different multipolarities. So for this analysis, I used those angular distributions. So I used the multipolarity L equal 1, the dipole multipolarity, L equal 2 for quadruple multipolarity, and L equal 2 for octuple states. And for each of those multipolarities, in the direct reaction model, we were able to distinguish between the isoscalar and the isovector contribution to concern the isospin quantum number to characterize the resonance. And so you have here, for each multipolarity, each color, two contribution, the solid line for the isovector contribution and the dashed line for the isoscalar contribution. So now that I have my theoretical prediction for the angular distribution of the different multipolarities and my experimental angular distribution of the elastic scattering channel, a multiple decomposition analysis can be made on the experimental point. That is to say, the experimental angular distribution is fitted with different contributions from all those curves. And via a chi-square minimization, each of the coefficients in front of those contributions can be extracted. And the coefficients related to the different multipolarities are directly related to the strength of the excitation. So here I show the results of the multiple decomposition analysis for the two slices in energy that I showed before. So you see in those fits contribution from the elastic scattering channel here with the gray solid line. And then you see the contribution from the different multipolarities with the different colors. And the total curve is represented with the black solid line. And so this analysis, this multiple decomposition analysis, was performed for each slice in energy. And for each slice in energy, the corresponding coefficients were extracted. So this brings me to the last part of this presentation, which concerns the interpretation of the result. And first, I would like to mention the result on the quadruple strength that was extracted. So as I said before, here you have the excitation energy. So for each slice in energy, you have a value of the coefficient, which is given. And this value here is given in terms of the energy weighted sum rule. So basically, the energy weighted sum rule is a theoretical tool to express the strength of the excitation. And here it is given as a percentage of the total energy weighted sum rule of up to 150 MeV, so on the whole energy range. And you have here the result of the quadruple contribution on the left for the isoscalar quadruple contribution, and on the right for the isovector quadruple contribution. And here the experimental values are compared with the non-2+ state of 140 cerium. So in particular here, if we look at the isoscalar quadruple strength, I extracted a contribution here that corresponds to the first non-2+ excited state of 140 cerium, which is located at 1.6 MeV. And the percentage of the energy weighted sum rule which is exhausted by this state is written here. It's around 9.5%. And if we compare this value with the QRPA prediction, they gave a total of around 11% of the energy weighted sum rule exhausted by this state, so which was a quite good agreement with the results. So just a comment here, the energy predicted by the QRPA is higher than the one experimentally observed, but this is expected within the framework of those predictions. So now let's move finally to the dipole strengths that were extracted. So you have here, just as for the quadruple contribution, on the left, the isoscalar dipole strength, and on the right, the isovector dipole strength. So the first state, which is populated, the first dipole state, which is populated, is this one located at around 3.6 MeV. And it indeed corresponds to the first known 1- state of 140 cerium at 3.6 MeV. But this state corresponds to a two-phonon mode of the first 2+ and the first 3- excited state of carbon and of cerium, sorry. And so it is excluded of this analysis because it does not correspond to a pygmy dipole resonance state. So from those graphs, first, I extracted the total energy weighted sum rule exhausted in the pygmy region, so between 4 and up to 9 MeV, that is to say up to the neutron separation energy threshold. And you have here the value that were extracted. So you see that the energy weighted sum rule exhausted for those low-lying 1- state corresponds to a few percent of the energy weighted sum rule, and which is what is expected for the pygmy state. So up to now, we are coherent with the definition of the PDR. And so now, as I said at the beginning, we can compare those results with previous results using other probes. So first, we can have a look at the isoscalar component of the PDR energy region. So you have here the results of this work, which are compared with the two isoscalar probes, alpha particle and oxygen-17. And those results with the neutron probe are in agreement with the previous result with other isoscalar probes, because you see that we again see a kind of an energy threshold above which we do not populate states up to the neutron separation energy threshold. So this threshold with the neutron probe is at around 7 MeV, so a bit higher than the one with the other isoscalar probes, which was at around 6.2 MeV. And if we now look at the isovector component in the pygmy region, you see that in agreement again with the other probes, we populate in the isovector response states up to 9 MeV, up to the neutron separation energy threshold. So if we now compare the difference probe more quantitatively, so I recall here the percentages of the energy-weighted sample that were exhausted with the neutron probe, and I give here the corresponding probability transition values just corresponded to those energy-weighted sample. Here, I compare those values with microscopic prediction within the QRPA and the QPM framework, so I will not enter into the details, but two microscopic prediction. And here, I give the values obtained in other experimental studies. So only the gamma-gamma prime and the oxygen-17 inelastic scattering gave the result in terms of those values. So if we first have a look at the isoscalar components, so we see that with the neutron probe, we have a lower energy-weighted sample and a lower probability transition than the one expected with the prediction, and that the one obtained with the isoscalar oxygen-17 probe. However, regarding the isovector component, we see that we are in quite good agreement with the microscopic prediction, and we have a higher isovector contribution than the gamma-gamma prime reaction. So this is a first interpretation in terms of the isospin component in the pygmy region. But I also said at the beginning that we wanted to use the complementarity of the neutron and the proton probes to extract information on the nature of the PDR state. And so to do so here I show the previous experimental results with the proton probe, which are given in terms of the differential cross-section as a function of the energy. And to be able to compare those results with the proton probe with my experimental results, I repeated the multiple decomposition analysis and the extraction of the strength, but this time without the distinction between isoscalar and isovector components, because here there is no such distinction. So I simply use in my multiple decomposition analysis the elastic scattering contribution and the total contribution from the dipole, quadrupole, and octuple strength. And you have here the results of the total dipole strength exhausted in the pygmy region with the neutron probe in terms of the differential cross-section. And now from those two results, we can think of a way to extract information on the nature of the PDR state. So this is the last thing which is to be done regarding the analysis that I will do in the coming weeks. And the procedure will be the following. So as I said at the beginning, the microscopic description of the PDR state can be made in terms of the transition density of the protons and of the neutrons with respect to the ground state density. So here I show just a transition density for the first 1- state predicted within the QRPA framework with the relative contribution of protons and neutrons. And the goal now will be for us to generate transition density, so independently of microscopic models, and to play with the relative contribution to proton and neutrons. So since we know that the proton and the neutron probe have complementarity, also sensitivity to those contributions. So for instance, we can multiply by 3 the contribution of the neutron and see how it changes the cross-section and the results. And so for all the transition density that we will generate, the DWBA calculations will be applied for both the proton and the neutron probe, and the differential cross-section will be extracted. And from those predictions, we will see if we can reproduce the experimental data at the same time for the proton and the neutron contribution. If no, we can change the transition density, and if yes, we can extract more information on the nature of the excited state and then compare it with the microscopic prediction. So this is to be done in the coming weeks. So this brings me to my conclusion. So I presented here the first study of the pygmy dipole resonance via neutron inelastic scattering, an experiment performed at the Neutron for Science facility. And from this analysis, the dipole strength was extracted with the scattered neutron angular distribution, relying on microscopic QRPA prediction and DWBA calculation. And first results were obtained regarding the isospin content in the PDR energy region and were in agreement with the previous studies. So we saw that the PDR state exhausted a few % of the energy-weighted sample as expected. The isoscalar components showed kind of a threshold above which no more isoscalar states were populated, a threshold a bit higher than the one previously measured. And the isovector component was extended up to the neutron separation energy threshold, so in the whole PDR energy region. And what is now still to be done is to use the complementarity of the proton and the neutron probes to pin down the structure of the PDR state and then compare the structure extracted with the microscopic prediction. So this is the last part of this analysis. And regarding the experiments, so there were a letter of intent, which was deposited for a next experiment for the study of the PDR at NFS, maybe on 208 bismuth. So this is all on my side, and I thank you for your attention.